This is a review of the A level for marine science, paper 3, version 2. And this is from May, June 2022. And these are all available online. So if you want to also do this with me for studying purposes for your paper tomorrow, follow along. You can print them out, or you could do it electronically on a tablet. All right. As always, use dark black or blue pen, not a gel pen because it could smear, and pencil for any diagrams or graphs or anything that you need to label. A bit bigger. Okay. First one, we're looking at parts of a cell. It's a typical plant cell from a mangrove tree, and you're seeing under an electron microscope. And the first question we have is state 3 features that is visible that shows that this is a plant cell. And so right away, one of those features, I think it's most obvious, is going to be the cell wall on the outside. All right, another massive thing that's here, it's only visible in a plant cell, is the large permanent vacuole. And I think another obvious one is going to be the presence of chloroplasts for photosynthesis, so something to absorb light energy. And those will be our 3. And the cell wall is always on the outside, and then on the inside is the cell membrane. It does prevent it from bursting. And permanent is underlined. So that is the word that we need to make sure that we have for the vacuole, is a large permanent vacuole. Name the structures A, B, and C, and D on the figure, and then write your answers on figure 1.1, which is the actual picture. This is figure 1.1, A, B, C, and D. And so A is pointing to the inner membrane, and that's actually going to be the cell membrane. B has the presence of ribosomes on it, and this is the rough endoplasmic reticulum. C, you can see all those inner folds called the cristae, and that is where glucose gets oxidized and ATP gets synthesized. This is the mitochondria. And then our last one is this, looks like a wishbone. It's the wishbone of the cell. No, that's not it. Sometimes this one is difficult to identify, and this is why in the syllabus it says be able to identify from diagrams or from actual microscopy. Or if they're being described, also be able to identify what parts those are. But if we compare where everything else is, this is just going to be the smooth endoplasmic reticulum. All right, the next question, outline. So outline is just like a short description. Outline the functions of structures E, F, and G, 3 marks. E, F, and G. And first I'll label them. So E is pointing to the Golgi body, or you could say Golgi apparatus. And it looks like pancakes folded on themselves, or like a Wi-Fi signal. F, just those dots, those are ribosomes. And G is pointing to the nucleus. Okay, and this is just, it's not 6 marks, so you have to like state the structure and then outline their functions. It is just outline their functions. So structure E is going to be the Golgi apparatus, and that is going, we could say collect and process molecules molecules. Processed proteins in vesicles with one S. For export, or again, a very easy one to write is this makes lysosomes or synthesizes lysosomes. And lysosomes destroy things that are within the cell. Structure F is just your ribosome, so that's protein synthesis. They synthesize proteins. Structure G is the DNA, so this we could say contains chromosomes. You could also say chromatin. So that's actually the structure DNA is in when the cell's not dividing. When the cell is dividing, they make chromosomes, right? And they usually look like this, like those little X's. Those would be chromosomes. Otherwise, chromatin is just completely unwound genetic material. So it contains chromosomes. We could say DNA, or instructions that determine, or just things that determine. Goodness, it's hard to write and talk. Proteins. Okay, and then to end the cell questions, describe how, so like what, how phospholipids are arranged in cell membranes. So it's not explain, it's just describe how. Okay, and so back to my other video, right? I said sometimes I draw a heart just as a reminder. And that's because they are hydrophilic, which means they love water. And those are the phosphate heads. And they point outwards. They're hydrophilic. And then the fatty acid tails are hydrophobic. So they are nonpolar and they do not bond with water or polar things. And that's why we need to have like big proteins built in, maybe like a carrier protein, so we can bring things into and out of the cell that are charged molecules or are also polar. Okay. They'll say they form a bilayer. Here's your one, here's your bi. Second thing. And I'm sorry, I'm going to say phosphate head instead. Hydrophilic, and it faces the outside of the cell, and that means that it's polar. Those two things need to be there, those two statements. And then we have fatty acid tails. Are hydrophobic. They do not bond with water or any other polar charged molecules. And they face inwards. And if you don't want to say hydrophobic, you could say that they're nonpolar. Same here, we could say that the phosphate heads are polar. All right, so on to some photosynthesis, everybody's favorite. Kidding. All right, and this one got the Kelvin cycle, and so I think if you are taking paper 1, I'm sorry, that means paper 3, time zone 1, So if you're taking 3-1 tomorrow, um, your time zone has yet to be tested over the Kelvin cycle or the light independent reaction, which occurs in the stroma. So that should be something that you should expect. Whereas if you took paper, if you're taking paper 3 version 2, so 3-2 tomorrow, your time zone has yet to be tested on the light dependent reaction that happens in the thylakoid membranes. And so that is something that you should probably expect to see tomorrow. With the newer syllabus, that's kind of a lucky or good way to be able to look at it. What was tested last year for your specific time zone wasn't tested yet in the other time zone. If you're in time zone 3, so you take paper 3-3, your test is typically the same as paper 3-2, and so you should expect to see the opposite. Again, from what your time zone tested on last year, they're not really gonna, they have to at least go ahead and test what you haven't seen yet. So that's something to consider. Okay. Here's one of the stages involving photosynthesis. And so this is the Calvin cycle, and this is happening in the stroma. And the Calvin cycle, I always, just for myself, I refer to it as the C cycle. And I'll show you why. Because you have, it's the Calvin cycle, but you have CO2, and it's synthesizing C6H12O6. So that's why I call it the C cycle, because it's the Calvin cycle, and this is where CO2 comes in, and then glucose is synthesized and released. All right, so first we have CO2 brought in through the stomas or stomata that are underneath the leaf, so it just diffuses in. And with rubisco, so that is an enzyme. Enzymes make things go, and A is going to be rubisco. You don't need to know like what it stands for or writing out its whole name. Okay, a 6-carbon compound gets made, and that is very unstable. And so right away, it breaks down into 2 3-carbon compounds. So you get 2 3-carbon compounds. And this 6-carbon compound that's made right in the beginning is not glucose. And here, where we're at B, this is where the electron carrier, NADP, but carrying hydrogen, because we're going to need hydrogen and glucose. This is where the hydrogen is going to get dropped off, and now we just send back the NADP without its hydrogen. It's going to be going back to it's going to be going back to the light dependent reaction after it drops off that hydrogen. Or you can call this NADP reduced because it is bringing on high energy electrons. All right, and we can't write here, we're not going to write NADP. There we go. We're not just going to put NADP because it needs to bring the hydrogen. We need to include that. It really doesn't leave until it's dropped this off. All right, and then it takes energy to bring that here. And so this C is going to be ATP. The NADPH with energy from ATP is going to combine with CO2. And out of these 2 3-carbon compounds, we're going to actually release glucose. And then this is like the reforming and like rebuilding of RUBP. RUBP is a 5-carbon compound sugar, and it is going to reform with this CO2 all over again. So this is like the starting building block for the Calvin cycle. And so in order for this to be able to run through again and be able to synthesize more glucose, we need to have this reformed after glucose is made. So after D happens, we need to get ready with our main ingredient again so that when more CO2 does come in, Rubisco is able to combine CO2 and the RUBP to form that 6-carbon sugar. And then we're going to break it down. Again, we're going to drop off the hydrogen from the NADPH, and that hydrogen is the result of photolysis, happens in the thylakoids, where the energy gets absorbed in thylakoids, and then we split the water molecule, photolysis, oxygen gets released, the hydrogen comes over to the Calvin cycle in the stroma. It takes energy to start forming our glucose molecule that we see at D, and then we need to use energy again to reform the RUBP, so that, again, we can do this all over again. So name the stage where this occurs in the chloroplast. Name the enzyme at A, that's the go. What makes things go is Rubisco. It's not Rubisco, but I think it's easy to think of it like that. It is Rubisco because it is a coenzyme. And there's a compound at B, a compound at C, and a compound at D. And now, unlike the paper 3-1, it does matter what you do put in for these answers in the orders. So this is called the Calvin cycle, or you can refer to it as the light independent stage. And it occurs in the stroma. The stroma is the fluid portion of the chloroplast. So we have these connected to each other. So everything that's like right here would be the stroma. Everything that's like it would be like the cytoplasm of the chloroplast. Our enzyme is Rubisco. The compound at B is NADPH, or you can call it NADP reduced, because it's carrying those electrons, which reduce it. The compound at C is going to be ATP. Takes energy to reform the RUBP, which starts this whole thing off. And then the compound at D is what actually gets created and comes out of the Calvin cycle completely. That is glucose. Okay, a little bit of limiting factors. So we're seeing the effect of temperature on the rate or the speed of photosynthesis in a mangrove leaf, and you're at a constant CO2 concentration of 0.1%. So again, we're going to be looking at the describe and explain. So what do you see and why? What is the graph doing? Explain why it's doing that. The effect of temperature on the rate of photosynthesis. All right, and things you can notice as temperature starts to increase, it's a positive correlation, the rate of photosynthesis also increases. But then we get to an area where we're at an optimum temperature, and any further increase in temperature this direction is going to cause the rate of photosynthesis to plummet pretty quick. So obviously you should be thinking that, like, why is it going down? We have enzymes denaturing at that point. So even though we have CO2 there, and we know that CO2 is combined with RUBP, and the enzyme Rubisco is what combines them, it doesn't matter, because past this point, this optimum temperature, the Rubisco, for example, is denaturing, which means it's changing its shape. So it's no longer able to catalyze or speed up the same reactions that it has in the past. Additionally, if we're looking at the CO2 concentration, If we increase temp, that's going to cause a decrease in gas solubility. And that's from chapter 1, section 2 of the AS level syllabus. All right, so we need to go with describe what we see. We need to take care of this first part. It's increasing, why, and then what happens down here. So as temperature increases, the rate of photosynthesis increases, and you're able to actually discuss out or state this entire trend initially, but then you just need to make sure you talk about why it does increase and then why it does decrease pretty quick. So for example, you could say as temperature increases, the rate of photosynthesis increases until an optimum, and then as temperature increases past that, the rate of photosynthesis slows down or stops, decreases really fast. So this is like your what, this is a describe. And why does this happen? An increase in temperature causes an increase in kinetic energy. So particle movement's faster, molecule movement's faster, enzyme movement is faster. Okay, E is kinetic energy. Or you could be more specific and say there's more molecule collisions. Literally, they're just moving around a lot faster. That's like a mosh pit versus a slow dance. Between Rubisco and CO2 and RUBP. And it's Rubisco that's putting together the CO2 and the RUBP. Rubisco is joining them. It's catalyzing or speeding up that reaction. This is the explain. And now I need to talk about what happens when I hit that optimum. What do we see this graph doing? It's decreasing. So we need to discuss that second part. Again, this is going to be like the what? So after an optimum temp, an increase in temperature, or after temperature is at an optimum, you can also say that, an increase in temperature causes you can say rapid, but you don't have to, a rapid decrease in the rate of photosynthesis. And tomorrow, Monday, or whenever you guys have your exam, we're not going to put NRG. You don't want to put arrows. We're not just going to say photo. We're going to say photosynthesis. And this is your why. Enzymes, and specifically Rubisco, denatures, which means it changes its shape. Additionally, an increase in temperature, so you don't have to say both these things, but an increase in temperature causes low gas or CO2 solubility. And they say the CO2 concentration in the mangrove leaf was increased to 0.5%, and right now we read that it's at 0.1. Sketch a line to show what you would expect happen to the rate of photosynthesis. So it doesn't change the optimum temperature. I'm going to erase these. It's not going to change the optimum temperature. What is going to happen though is, there you go. Initially, like we're going to have higher rate of photosynthesis anyways. CO2 is a limiting factor. So the entire line should have an increase in the rate. And you can see that by drawing it above it. And we're going to hit that optimum temperature. And just because there's more CO2 doesn't mean that it's not going to denature. It's still going to denature at the same area. But again, because there was more CO2 to be like combining with RUBP in the light independent phase, then we're still going to be able to actually carry out more photosynthesis, just even though it's denaturing. And then a reason for the line. CO2 is a limiting factor. In photosynthesis. Or we could say if we increase CO2, the rate of photo increases. Okay, the next one we're going to be looking at some sustainable fishing questions. There's actually a lot of information within just these couple of passages. Skipjack tuna occur in large shoals, so those are like schools of fish, but it's when they're swimming for like a social purpose. So whether it's for getting a mate or to avoid predation or to find a food source, increase their own hydrodynamic efficiency so they can swim faster. And so they occur in large shoals in tropical and subtropical, so not as hot, more maybe seasonal places, areas. It's not temperate though. I take that back. It's not seasonal. It's not temperate. It's subtropical. Areas around the coast of West Africa, and that's not very specific. They're not saying specifically where. Like maybe there's a breeding ground specific or a nursery specifically that's not being mentioned. They reach sexual maturity in 1 year, and they spawn throughout the year. So they don't have a specific season of spawning. In tropical areas where temperature is at least 25 degrees Celsius. So they spawn in tropical areas and the temperature is at least 25. Data from tagged fish, so they do have some tagging there, which would help with identifying their population changes or any changes to recruitment. Recruitment is measurement of the amount of fish that are entering the habitat. So that's from migration, births. Okay. Also, like takes into account fecundity, like how fertile and how many eggs and how often organisms are going to reproduce, what age they reach sexual maturity. Data from tagged fish have shown that the growth of skipjack tuna from subtropical areas is faster than in tropical areas. Suggests a reason for the difference in growth rates. And so, I mean, right away, the first thing about subtropical, so it's not in the tropics, it's outside of that. So it's going to be a little bit cooler water. And colder water, it's going to comparatively to tropical areas, to warmer water, cooler water is going to have more oxygen solubility. And so the fish will be able to do respiration more, and it'll allow them to grow. Now, when we're answering this question, we need to talk about this answer in terms of growth rates. So we can't just say there's going to be more oxygen dissolved. We need to say there's more oxygen dissolved, so they're going to be able to do respiration and have energy for growth. Something else we could talk about is that typically in subtropical areas, and we do have this off the west coast of Africa, this also happens off the west coast of Ecuador and Peru, you have upwelling from trade winds blowing across. So more upwelling is going to allow for more nutrients, and more nutrients are going to allow for more growth because you're going to have more productivity of producers, and so the entire food webs will improve. If there's more food available, more of a food source available in subtropical areas, then we could also talk about there being less competition for food and there will be more growth. So we're not just gonna, we don't just want to say like state, like this, this thing happens. We need to then say this thing happens and this is how it's going to allow for more growth rates. And this is only one mark too. So if you didn't get the whole thing, that's honestly okay. It's just one. So first thing I'm going to talk about is there's more oxygen available in subtropics. So more oxygen will mean more respiration. And if there's more respiration, then we'll have like more energy for growth. Okay, another one we can mention, I'm actually going to get rid of that so I can do one that's yeah. There we go. So one that I can actually not have all the background in. More upwelling in subtropics. So we're going to have more nutrients for primary or for producer productivity. And that will allow for more food. All the trophic levels benefit. And just in general, there will be more food, there could be more food available in subtropics, so then we won't have as much competition for food. So there will be more to eat and they're going to be able to grow faster. Okay, and then keep in mind where we mentioned they just said around the coast of West Africa, nothing very specific. They spawn throughout the year. So there's not like one specific breeding time that we can maybe restrict because they are spawning throughout the year and it'd be hard to manage their populations. Before 1990, most skipjack tuna fishing occurred from small local boats using long lines or a pole and a line. Those things are very sustainable. Long lines, so there's your water. Long lines could, though it's not the best, because we can get a lot of bycatch on hooks. They kind of dangle like this, and they're all connected. They float, and you got a hook at the bottom. All right, and so they can float, or you could have pelagic long lines, so like middle of the ocean. They float them like in the middle. So now it's something more like this, and this is much more dangerous because you can have a lot of transient organisms getting stuck on those, and they get caught. Those are your long lines. But then they also did pole and line, or they said like more traditional methods before 1990. Now, since 1990, modern technology like sonar and Percene nets on industrial fishing fleets, so not just local. Before they said small local boats, now we're at industrial fishing fleets. That has increased the number and the size of the fishing area. So there's more fishing areas and they are also larger. They can also be further from the coast. Large shoals are usually a mix of skipjack tuna and other shoaling species. Shoals that form under the fish aggregation devices, or FADs, FADs, consist of a much higher percentage of skipjack tuna. So this is probably something they're going to implement a lot. You see the total skipjack tuna catch from all fishing methods, so totaled, in West Africa between 2010 and 2017. All right, and so between, and I already did the subtraction, the comparison, in a 3-year period, they increased their fish catches by 102,687 tons. That's your unit right there. And then between 2013 and 2014, so a 4-year period, they increased by 12,713 tons. And now there isn't a question that asks this, but if it says like suggest a reason for the differences in what was caught between those 7 years, well, one thing I would say is I would definitely give like a number example, just like what I gave you. And I would say that they've overfished and fished out too many juveniles and the adults between 2010 and 2013, so there weren't enough to reproduce in 2017. But you do not have a question like that, but it's something that I was expecting, honestly. At the graph, we see the average skipjack tuna catch by purse seine fishing only, with and without the use of fish aggregating devices for that 7-year period. Fish aggregating devices encourage the fish to shoal in that area. And so we see a pretty big difference here. For example, in 2012, and if we look to, just to see what we're counting by, we have 5 different 5 lines. So our number 5 is being split up 5 ways, and so each box is equal to 1, which is pretty easy. So in 2012, without using an FAD, we are at about, I'm gonna call it 5 tons of fish. 2012 we'll go with, and then without the FAD. And now with the FAD, we are at 25 point, I'm going to call it 25.5. So 25.5 divided by 5, just so we can compare, it's 5.1. So using a fish aggregating device in 2012, you had an increase, it was like you had 5.1 times the amount of fish you would get versus not having a fish aggregating device. We could do the same in 2014. So again, we're at 5 for without. Versus with 31. 31 divided by 5, we're gonna have just a little bit over 6. 6.2 times the amount. And we could do the same thing for 2017, which is right here. 2017, we had 6. So with and without the fish aggregating device, without we had 6. And then with, we are at 31, 32.5. Okay, and that is 5.4. So anywhere from, it seems to be like greater than a 5% times the amount of catch. If you were just using, or without using an FAD, you get 5, or with using an FAD compared to not using it, you get about 5 times the amount of catch. So 6.2, 5.4, 5.1. Use all the information. suggest and explain why there's been an increase in total catch in 2000 since 2010. So, what do you think? And then, why do you think that there's been an increase in the total catch since 2010? They say use the information, so we will use the information. For example, we can use the amount that the catch has increased with using a fish aggregating device. And so they did mention that there's been a change in gear from using like a rod and line, which is the most sustainable. You can only catch one at a time. It prevents overfishing. But we're using from using a pole and a line or rod and line to now purse seines. So the change in your fishing method. Okay, and so explain that. Why is a purse seine going to be causing the increase? Purse seines can catch the entire shoal at once. Another reason, so the use of sonar. To detect the size or the depth or the location of the shoal. They have the advantage of using industrial boats. Just so you can see where I'm getting that from. They said since 1990, modern technology like sonar, purse seine nets, and then the industrial fishing boats has increased. Both the number and fishing areas, so the amount of fishing areas and how wide they are. Okay, so this again is the suggest. This is like your why, and this is the explain. The use of fish aggregating devices. And they said, before I write it so you can see where it's coming from, there's a higher percentage of skipjack tuna forming under the fish aggregating devices. So they increase the percent of skipjack tuna. And then again, use the data. So around 5 to 6 times more than no FAD use. Scientists are concerned that skipjack tuna fishing might now be unsustainable. State the meaning of the term unsustainable. So this is also a definition from that section. This is fishing past the maximum sustainable yield. So the amount of fish that could be caught will still allow to maintain populations for the future. Or something to describe that. So something describing that current catch amounts will prevent sufficient amount of fish or tuna breeding in the future. There won't be enough. State 2 restriction, so only 2 will be graded, just the first 2, that could be introduced to fishing gear. So we're not talking about quotas or having, I don't know. It's not gear. I was going to say maybe forcing them to have like an e-license, fishing gear to ensure that skipjack tuna stocks are sustainable. So this is going to be limits on their gear. So first thing I think about is within like the purse seam, and one of your vocab words as well, minimum mesh size. Introduce minimum mesh sizes, or tell them that they need to increase the mesh size so that your juveniles are able to escape. So increase that. That's so smaller fish can escape. Just in general, the length and the size, like specifically the size of the long lines. They might be way too big and it's catching just way too much fish inside of it. So if we can have them have to decrease the length or the size of the, I don't mean to say long lines, the purse seam. Decrease the length or size of purse seam. This will cause them to not be able to catch as much fish, or enforce use of rod and line fishing because you can only catch one at a time. It's the most sustainable method. So data on skipjack tuna stocks are limited, especially before 2010, and that could be like because of technology. Maybe they don't have ebooks or things like that. Even in 2017, catch was estimated to be underreported around 28%. And remember, fishermen might be dishonest. They want to avoid fines. They also want to avoid further restrictions or strict quotas. Use all the information provided in your own knowledge. Suggest why data on stock assessment of skipjack tuna are difficult to collect and are underreported. And that also includes wanting to avoid fines from catching bycatch. And one of the ways that they try and manage their population size, they can have something to base it off of, is, well, the data, their logbooks. And they also said in the beginning, they were tagged. There we go. Data from tagged fish show that they grow faster. Okay, so, and one of the things as well that we also identified at the top, they spawn throughout the year. So there's not just, like I said, a specific breeding period that we could limit their fishing. They restrict their fishing. They breed all year long. And it's very general. They just say around the coast of West Africa. There's not like a specific breeding ground that they can limit that. So it's a big area. So the tuna spawn or reproduce throughout the year. Within that, there is no specific breeding ground. So that's going to make it difficult to monitor. I think some of the easiest ones is the next marked logbooks, maybe incomplete, or done dishonestly. And then we need to say why we would be suggesting that, because this would decrease the chances of restrictions being introduced. They want to avoid fines. They want to avoid overfishing above their quota, provided they have one. And the other one that I said that I'm not going to list, but it's that they want to avoid, you know, being honest about fishing over their quota. Additionally, in their logbooks, bycatch, juveniles or undersized fish, or if there's damage to the tuna, that are thrown back, may not be reported. For the same reasons, bycatch is going to cost you, it's going to cause fines, and they know this. Catching juveniles, so catching below the stated legal size limit, and they are damaging tuna and throwing them back, and they're not worth keeping. That would be reported in like your bycatch or like the discards that you have. That would all go towards your ultimate quota, and they obviously don't want that to happen, because then there will be fines if they go past it. Perhaps not enough fish have been tagged with like a satellite tag. To monitor population changes. There's little data on natural mortality. And so within their mortality, we have mortality from fishing. So this is what was taken out of the ocean, both as bycatch, damaged fish, and fish that they're going to go sell and actually harvest. And then there's also natural mortality. So what's causing them to die over there? So there would just need to be more research done on it. There's a lack of air and sea patrol. Or even like port or marina. Monitoring. They're expensive and they are difficult to implement. Okay, so those are plenty. Got a blank page, and now we're on to renewable energy sources and the impact from that, which is in section 9.1. So the number of offshore wind farms are increasing annually. The wind power is converted to electricity by the turbines. You're going to have more than 650 turbines in the largest wind farms. State 2 reasons why the number of wind farms is increasing worldwide. Avoid saying population's increasing, because that isn't saying anything about wind farms. So population's increasing and you're saying that there's more of an energy demand, then say there's more of an energy demand. Don't say because wind farms are environmentally friendly. What does that mean? Same with they're green. What does that mean that they're green? Their color's actually green. If you're implying that they are better for the environment or environmentally friendly because they don't release carbon dioxide or greenhouse gases, or they are renewable, then that's what you need to state for it. So you could have the demand for energy is increasing. Again, something we're not going to write on Monday. It's renewable, or it's a sustainable energy source, or it doesn't use fossil fuels. Renewable or sustainable. We could say there's no, but that's not entirely true. So less CO2, because there will be CO2 released like in their creation in like a factory. And boats need to be bringing these over into like their specific location in the ocean. And the boats are going to be running off fossil fuels. So we could saying no isn't entirely accurate. Saying less is a little bit better. Release in the atmosphere, ATM. Along this, you could also say there's less of a carbon footprint. There's less effect on global warming for those same reasons. And you could also state that for ocean acidification as well. And lastly, there could be legislation or new laws passed that like demand that we have less of emissions in the atmosphere. Emissions. All right, so we're looking at two turbines from an offshore wind farm. We have a generator that uses wind energy, generates electricity using electromagnetism. Okay, and so that could like mess up migration routes. Um, the energy or the noise that it makes maybe could disturb or disrupt fish or disrupt eggs or larvae. The blade length can be 40 meters or more. And depending on what the questions will ask, that's something I consider with birds getting caught. The shaft turbine is placed into a steel tube for support. These actually act as FADs, fish aggregating devices. The steel tube is 4 meters in diameter, which is really wide, and it's hammered 25 meters into the seabed. And so this just gives me some things to write about for dislodges sediment, and then it's going to cause increase in turbidity, could get stuck in fish gills, could decrease their food source because your producers are going to have more turbidity, they won't get as much sunlight. We could also dislodge organisms or larvae, and we could completely damage the seabed or any benthic organisms down there. So during construction, the steel tubes are placed into the seabed either by drilling in rocky areas or being hammered into the sediment. So there's all your dislodging sediment. I imagine it's loud. The vibrations from the sound and the hammering again could destroy eggs or larvae. The noise could be confusing to fish. It could cause them just to up and leave the entire area and migrate away. Large ships bring the parts to the site for assembly. They lay cables to transport electricity generated from the wind farm to the land. And the cable laying could also cause disruption in the seabed, like directly, or organisms that live there. 3 marks. So what are the likely impacts of construction activities on marine fish, and explain your reasoning. So what is your suggest or what is the impacts, and then why did you say that? Okay, so just in general, there could be a loss in feeding, breeding, or nursery grounds. Yep, loss of feeding, breeding, or nursery areas. And this would decrease fish numbers, fish population. The electromagnetic field that was mentioned right here. Or loud hammering or drilling. Can drive fish away. Like they would just want to avoid that area altogether. Sound vibrations, or from the drilling or from the hammering, may damage fish eggs or larvae. Again, could cause the fish to migrate. And we're answering in terms of fish because it does say impacts of construction activities on marine fish. In general, existing migration routes could change. So separately from fish just leaving, or they can migrate away, if there already is an existing migration season that's going through that area, that could change. And then we have high sediment, or the turbidity. And an effect on organisms. So for this, I would say about decreasing photosynthesis because it's not going to have as much light penetration. I'm not going to write out the entirety of where these marks would be. They're very repetitive from other questions, but we're going to decrease photosynthesis. So that's going to cause a lack of food source. Fish numbers will decrease. We could also say this will clog gills. Fish won't be able to do respiration, or they're going to lose surface area on their gill surface to be able to do respiration and be able to extract oxygen from the water. This could disrupt, like that more sediment and turbidity disrupts toxins that are in the seabed. And that will cause bioaccumulation. Again, increase in sediment. And if you want to go into the bioaccumulation and then, it's magnifying up trophic levels, and that could cause a disruption in hormones or reproductive behavior, then keep going. So this one is specifically about releasing toxins that could kill fish. So whether this is from disrupting the sediment or the construction materials used. And this is from the sediment getting dislodged or disrupted from hammering or drilling into rocks. Kill the fish. Just make sure that we're saying the activities on marine fish, how it affects the fish. Laying the cables. Or the steel tubing. Could just straight up ruin benthic habitats where fish would live. And not just necessarily benthic habitats, but could dislodge from the sediment benthic organisms. Several different methods are used to protect the base of the turbine from erosion by water currents. These methods include placing large 2-meter structures, either large rocks or the reef ball around the base. It's the typical reef ball. And this is also used in artificial reefs. and it allows fish to be able to swim through, hide from predators, and it is like a hard, rough surface, so you can have some like coral start to attach to it, start to build up a lovely little food web here. And if we consider like water flowing, if water was just like hitting like a rough edge, that would be taking on like a lot of erosion and a lot of water pressure right here. But instead, like water is able to flow through these, and it does dissipate a bit of the current and stop all of that, the force of water, versus if it's just like a flat edge, like if it was just a rock. So the reef ball having holes does allow water to flow through and does prevent so much like um, um, pressure from the water hitting it. All right, so just the ecological advantage of using a reef ball instead of using large rocks. Again, a reef ball does encourage artificial reefs to form. So there's more surface area for attachment of organisms, and they can also attach like within the holes, like on the insides here, and not just on the outside. There's going to be more habitat available, just like an artificial reef. Okay, and a little bit more specifically, the holes, like in terms of like where is there more habitat with more being underlined on the syllabus or on this mark scheme, the holes will provide hiding places or protection, more breeding areas, again, versus if it was just a rock. And this will increase the biodiversity over time. Again, with the holes can dissipate the energy from currents, or have less, that the word I was looking for before was resistance, not pressure, but less resistance than using rocks. And that will decrease erosion on it. However, or not however, sorry, in using rocks, digging or quarrying or mining for rocks disturbs, or actually I'm going to say causes, ecological damage. And reef balls obviously won't. Suggests an advantage and a disadvantage of large offshore wind farms to commercial fishermen. So this is in terms of commercial fishermen. Your advantages, these could become a refuge for fish to breed, especially if there's reef balls there. Another advantage is that these act like fish aggregating devices, and that's in the textbook as well. This could increase fish numbers in surrounding areas, like if they spill over. Now, a downside, the disadvantages. We could have, just in general, loss of fishing area because of the wind farms. And then because of this, so because of what we just said, this would cause an increase in competition, so competition between fisheries. Having reef balls or rocks holding down those steel tubes that could damage fishing nets. Another one is that the cords and the long cables, there we go, that are laid on the seabed could damage benthic trawlers. Like, who cares? Let them damage all the benthic trawlers. It's the most destructive form of fishing, and like up to 90, anywhere from like 80, 90% of what they catch is not intended to be caught. It's like bycatch. And that's like in the same mark. How about damage to their equipment? Cables can damage benthic trawlers. Fish migrate away from vibrations from the entire machinery or from the construction of it. So we have two sides of that. They could act as fish aggregating devices, but then all of the vibrations from them, whether it's with the construction of it or the actual establishment of it, like the day-to-day use, could cause them to also migrate. And if they do have to navigate around it, fuel costs could increase. All right. Now we're in section B. So the bigger mark questions, and so that means we're about more than halfway. So this is going to be from 8.3, which is aquaculture. And then you got a 9.2, explain the natural greenhouse effect and how it makes life suitable on Earth. I already put in this answer because I've already written it once. It is a massive answer, but like I said in the other video, it is worth going over because they are very easy marks for increasing seawater temperatures on the marine environment. And the last one is about conservation can increase biodiversity. Discuss the importance of marine biodiversity in terms of the service it provides, which is extremely A-level type question. Very 4.3 of them to include this. I don't know how I feel about that. If we look at the October-November paper that they did for A-level, the theory paper, so which is paper 3, any of the versions, they were all the same. They asked about the difference between sharks and cartilaginous fish. That's literally the same thing. Hold on. Bony fish and cartilaginous fish, they're in the same kingdom, Animalia, or they're in the same phylum, rather, Chordata, but they're in different classes. And why would that be? I don't know how I feel about that because this is like the first time that I've ever seen an A-level paper test directly on AS level topics like that. You know, you could obviously expect students in A level to be able to talk about like increasing salinity will cause less oxygen. If you have an increase in temperature, you're going to have more evaporation. Salinity will go up, and that will cause less oxygen or less gas solubility. Like those topics can obviously come into play, but you wouldn't see a question that just says, you know, state the factors that could cause salinity to change. That is very AS level, and I don't know how I feel about it. I don't know. And looking at the examiner report, that's something that they mentioned, like, candidates really didn't do really well on this question. Talking about the one about sharks and bony fish. Well, probably because they didn't specifically, again, brush up on those differences. And they're really not discussed again in the A-level syllabus at all. So, yeah, that kind of goes to my thoughts on how many eggs are you putting in what basket? And that studying through AS level topics again is not really a basket that I would be putting a ton of eggs into. So that's my thoughts. Salmon farmers usually transfer smolt or juvenile fish from land-based hatcheries to sea cages in shallow inshore waters to go to adult size. As the availability of inshore sites decreases, several aquaculture businesses are looking at completing the growth process further offshore, and that's what this is going to focus on, in deep water cages and open ocean sites. So we see a possible deep water cage system, and it's monitored from land. So something to identify: the cage is fully sealed. That would mean we get to talk about less parasites, less escape, less disease influence, no algal blooms affecting them. Groups of 3 tubes to supply power and food to each cage and to remove waste products from the base of the cage. That's expensive and very dependent on electricity. But you also don't have to take a boat out there every time to feed and remove waste. But let's see, supply power and food to each. So one of the tube is doing food, another one is electricity, and the other one is to remove waste. So waste goes back, electricity goes to it, and then food goes to it. The sea cage is at 15 meters below the surface. However, the sea cage is connected to a winch, which will lower or raise the cage. That's really good because if you're in some like really bad weather, then you can also move them further down. There's a light unit under the cage that's going to be for the electricity, and that's going to be for boats to avoid hitting these or running into these. If they are massive ships and they are that deep, they're sinking that deep, which is common. And then one of a group of, and it's just an example of how many are in there, groups of up to 10 sea cages. So you've got a lot out there. So here's your group, and then there could be up to 10. Big mark question, 10 marks, but they're easy answers. So discuss the benefits and the challenges of growing your juvenile smolt to adult sizes in deep water sea cages in the open ocean sites instead of in shallow inshore waters. So we're going to be looking, I believe this one, again, would probably fall along the lines of you have to have, you can't have more than 6 suggestions or descriptions for one, like whether it's for the benefits or the challenges. So 6 and 4, or 4 and 6, but not 7 and then 3, because then you're kind of under evaluating the other one. All right, so our benefits and our challenges. It is 6 and 6. And if I have to go into the next page, I will. All right. She's a big one. It's gonna be more temperature stable than coastal water. So they said versus shallow inshore, so like closer to the coast. This is offshore, open ocean, where the parts near the coast, shallow waters are more able to have their temperature fluctuate. Open ocean typically does not. And temperature is necessary to maintain growth and oxygen amount. More temperature stable than shallow coastal waters. Because they are, I'm going to refer to it one more time, the cage is fully sealed unit. That's great. So because it's fully sealed, there's no chance of pollution from the cage escaping, like waste. And that could cause eutrophication, ton of bacterial growth. And they said that there was specifically a tube that's going to take that waste back. There is little effect on biodiversity. So I guess if there is any effect on it, it's going to be the organisms that would be like nectonic, which means you constantly swim, versus pelagic, which means you float. But maybe organisms that would be swimming through here are going to have to kind of go around it. But it really shouldn't have an effect on biodiversity. There is no, or again, less chance of predation. Maybe if like there was a really bad storm and it broke them open, then they could be preyed upon. Also includes parasites. No or less chance. So the quotes mean whatever I wrote above it, bring it down. A fish escape. And that's one of the things you really need to make sure doesn't happen, because then they become invasive. No chance of disease spreading to the wild population. So because there's so much that they're able to do from land, right? They're able to use a winch that can, lower this or bring it up. They're sending food over here, some electricity over here, and any waste is sent back. You don't have to bring as many boats there as often, so you're going to have less damage to like the seabed because you won't have as many anchors being put down from a boat. That would be a good thing. Less habitat damage, versus if they did this inshore. The cages can be lowered. In adverse weather, so maybe if there's really big waves and that's causing really strong currents. I can say this reduces damage to cages. No chance of algal blooms. ORG, organisms. Less chance of pollutants. Or toxins entering the cage. And because there's less visits, because a lot of this can be monitored on land, we're going to have less fuel being used. That little squiggle arrow, usually in my brain whenever I do it, that means this means, so less visits to cages, this means less fuel being used. Right, so if you had like more shallow inshore, not on land, but inshore cage system, you probably wouldn't invest all this money in technology and laying it on the seabed, like laying these tubes on the seabed to assist in feeding and removing waste. It might be something that you just, cost analysis figure out that you should just do, instead of having to implement all of these different tubes and laying down wires. So there's our benefits. And then I'm going to try to put it over here, the challenges, just so it's on the same page. And if you haven't seen any of my other videos, something that I do mention, you could always do like a T-chart in situations like this. Here you'd have benefits and here you'd have challenges. That is also something that you could do. And I will put this in a different color so that it's not right on top of each other. Okay, so initially this whole thing looks extremely expensive. That's something that I see. Very expensive and very reliable on, like, or reliant, not reliable, but reliant on making sure electricity doesn't fail. So there is increased expenses. For setup in deep water or like the open ocean. You're going to have increased like maintenance or like just running it day to day. Maintenance. Or we could also refer to that as like running costs, like daily running costs. It's further distance. The distance, actually, the thing being talked about, not further, but the distance, to monitor or check on cages, or carry out maintenance if something's damaged. Also to harvest fish, because that's the whole point. Cages. They might not always be accessible. If it's bad weather and you are closer to the shoreline, with inshore cages, not on land, but closer to shore, so like coastal, you still might be able to reach them if you needed to in adverse weather, but this is much worse, and then you're going to have even higher seas, which are like waves if you're out in the open ocean. So in adverse weather, we might not be able to reach the cages. The cages, just to see, cages must be robust or reinforced to combat adverse weather. Prevent being tossed around at sea. Come on. The winch or whatever you're anchoring them down with also needs to be really strong to hold them in place against strong currents or bad weather. And that's something that kind of goes with this right here. The benefit is that we can lower these cages in adverse weather, but that winch needs to be really strong to combat currents. These are very dependent on power, so electricity and food supply. And they're very dependent on being monitored from land. Tubes on seafloor could damage the habitat. For benthic organisms, or the tubes could entangle. Marine animals. The light beacon or the light source needs to constantly stay on so it can avoid getting damaged by shipping or damaged by a boat. So they can see it in the water. And then if you have any other valid point benefits or challenges, you can also include them. But again, this would be benefits and challenges to growing them in open ocean, deeper water cages versus shallower inshore cages. And you just need 5 and 5. So the natural greenhouse effect and how this is going to maintain a nice, comfortable ambient life. All right, and this is also very similar to what you guys have in your AS environmental class if you take it. So it explains, that's why and how, the natural greenhouse effect helps maintain a temperature on Earth that is suitable for life. So we're just talking about the normal natural greenhouse effect. Okay, so we're going to have solar, or you could even state it as electromagnetic radiation, because that is what we're going to reference, is the electromagnetic spectrum a little bit, that short and long wave radiation, or infrared radiation, that's the heat that you feel, and that would be more of your longer wavelengths. So the electromagnetic radiation that passes through Earth's atmosphere, and that's what we're going to start with, is light that's going to come from the sun, radiation from the sun. So short waves are going to be like a separate mark in and of itself. So starting just with solar radiation, or you can say electromagnetic radiation. And just some of it does, right? The gamma and X-rays do get, and the higher ultraviolet wavelengths do get reflected off of our ozone layer. Let me get another mark for saying that this is short wave radiation. So higher energy radiation. Now some of it is absorbed by Earth's surface. Here's the atmosphere. I'm terrible at including continents. But some of it is absorbed by the surface. Okay, and then some of it's reflected back. And so we can feel that heat that's absorbed by the surface. That's why things on the ground get hotter. Higher up, higher elevation, like in a mountain, you could have snow caps, and even in the desert, you could have some snow capped areas because light gets absorbed first at the surface of Earth, and then can start to bounce back. So that's why we also decrease in temperature the higher elevation we are. And just another mark for you having a little more details. It's reflected back as long wave radiation, or has less energy than where it started. But this would be like your infrared, yes, your infrared light, which is like the heat that you feel, like an infrared lamp. So some of it does get reflected back as longer wavelength radiation. Okay, so far one, solar radiation will pass through Earth's atmosphere. It's a shortwave radiation, has high energy. Some of it gets absorbed by the surface. 2. Some of it gets reflected back. 3. All right. And then, and for that long wave, again, you can also call it infra, which means less than red. Infrared, less than the color red. It is longer wavelength or less energy than the actual visible color red. And as it does get reflected back off, it's going to warm the atmosphere, warm Earth's surface. All right. The infrared or long wave radiation, putting in parentheses just so you have context what I'm talking about, gets trapped by greenhouse gases. GHG, greenhouse gases. And so this would be like a 4. So those will be our gases. And then you can give an example of those greenhouse gases. CO2, NH4, methane? No, CH4. Is it? I think it's CH4. SO2, sulfur dioxide, NOx, nitrous oxides, H2O vapor, CO, carbon monoxide. Okay. And then ultimately, this is it. Like these gases are like, I think of it like in my head as like they're like putting on an extra blanket. So the more blankets you have on, the more jackets you have on, the more you're going to maintain temperature, in a body. So this will maintain a higher temperature than if you didn't have the greenhouse effect. And so this will help it maintain like a suitable life for Earth. Planets that don't have an atmosphere can't do this. Like it's not suitable because the temperature can fluctuate so much between, solar radiation and then not having solar radiation on an area. And there's nothing that is maintainable. Okay, and then so a higher temperature is maintained. Just for context, than like what I'm comparing it to, than without greenhouse gases. So the enhanced greenhouse effect, which this doesn't ask about, but the enhanced greenhouse effect just says that we are absorbing um, and maintaining more greenhouse gases than are being like removed. We're just adding to this even more. So we're putting on blankets and jackets at the same time and multiple of them when we already have a suitable blanket and jacket. We're just adding more and more and more. All right, easy question here, but there's so many answers. I just literally don't want to rewrite it. Describe the possible impacts of increasing seawater temperature on marine environment. And so the way that I've sorted these is on the left side, I kind of categorize them based on what the answers are referring to. So this could cause coral bleaching. This is like due to zooxanthellae being expelled. So it could cause coral bleaching. Zooxanthellae, that's inside of coral tissues, inside of coral polyps. They perform photosynthesis in this mutualistic relationship, get expelled, and this will result in no photosynthesis in that area because corals don't do photosynthesis. It's the zooxanthellae inside of them. And if you're not doing photosynthesis, then you're going to have less food for coral or less organic material for corals, and not just corals, but that is one of your main producers in that habitat. Sure, you can have other different producers, but that's your main producer there. And the first organism that is going to benefit from the coral doing photosynthesis is, oh, I just said what I said not to say, from the zooxanthellae doing photosynthesis is the coral animal itself. So they'll be the first organism that's going to lose out from the expulsion or the bleaching from zooxanthellae leaving. For changing in ranges in migration patterns, so where organisms are able to tolerate certain water temperatures and environments, this could cause changes to the range and distribution of organisms. They could migrate to more suitable cooler areas, and then they'd be in competition with native species or organisms that already naturally migrate there. Less food sources, easy. So food sources, for example, krill could become scarce or die out. Krill are very sensitive to temperature changes. Krill is your dominant organism in the Antarctic food web. Reproductive rates are lowered in warmer water. Sperm and egg are very sensitive to increase in temperatures. This will have lower populations of organisms and a lack of food sources for organisms if their food sources are not being able to reproduce. And of the eggs that do get created, if they are not being able to actually to grow and develop. Obviously, an increase in temperature, there will be less oxygen solubility in warmer water, and so organisms could suffocate. They're going to have a faster rate of ventilation, like they're just trying to gasp for air more, and so they're not going to be able to do cellular respiration as fast. Therefore, they're not going to have as much growth, and they'll be slower. All right, we have increases in salinity, and then again, oxygen solubility. So an increase in temperature is going to cause an increase in salinity because there's going to be a lot of evaporation. This will cause less oxygen solubility or a decrease in the solubility of oxygen. And if there's less oxygen available, again, there's not going to be as much oxygen to do respiration with, so organisms will suffocate. The increase in salinity specifically, again, can affect osmosis and will cause more of a water loss if there is a greater salinity gradient from what's in the atmosphere, not the atmosphere, what's in the environment, like in the water, to actually what's in the organism tissues. They will lose salt. I'm sorry, I'm almost done. It will lose water a lot faster, and take on salts as well. So this can affect osmosis or your water potential that are in cells. Ocean currents. This could just cause a change in your ocean currents, the increase in temperature. Your ocean currents or your deep water currents are dominated by changes in salinity. So, and not just salinity, but also changes in temperature. Okay. So that's the thermohaline circulation, thermo being temperature and haline being the amount of dissolved salts, like salinity, the halocline. Thermohaline circulation is what forces deep water circulation. So just by changes in temperature and salinity, that it's very slow, that water moves extremely slowly. Like one parcel of water would take about 1,000 years to get from where it started within the global ocean conveyor belt to where it back to that same starting place, about 1,000 years. Melting ice can increase coastal flooding, or you could talk about other answers, increasing the coastal flooding or something else because of sea ice. Maybe it's decreasing habitats for polar bears, breeding areas for polar bears, breeding areas for penguins, and for their eggs to hatch. Causing changes in productivity or the rate of organic material production. So this could increase producer productivity. So there's the one good thing that we just talked about so far, the one good thing. So producers could increase in productivity because it is warmer. And as we saw in the beginning of this test, an increase in temperature could cause an increase in the rate of photosynthesis, but you can't go past that optimum. And again, why? An increase in temperature could cause an increase in enzyme activity. So we could have more photosynthesis. We could have more of the rubisco enzyme reacting with RUBP, your starting building block, 5-carbon sugar, reacting with CO2 to synthesize, ultimately, the end of that, glucose. But the productivity changes could be so great that they do cause an increase in algal blooms, and this could cause eutrophication from all that algae dying, needing to be decomposed by bacteria. And the bacteria, now doing such a massive job to decompose, they are going to use up a lot of the oxygen, and this will cause hypoxia, which is very low oxygen areas. Big answer. And our last one, so this is one that I complained about initially. I think this is more of like an AS level question, but you know, the basket and how many eggs you're going to put in it. So I mean, it's worth going over, but I would focus way more on things that are directly in your syllabus. So conservation measures frequently to aim to maintain or increase biodiversity. Discuss the importance of biodiversity in terms of the services that it provides. And so we're thinking about services. The things that we want to talk about are stable ecosystems, climate control, shoreline or coastal protection, food and medicines. All right, when we talk about stable ecosystems, a really simple way to also describe that is that you can maintain your food webs and food chains. So stable ecosystems or maintaining your food webs, food chains, those are maintained. Examples. Oh, sorry, not examples. I'm going to talk about coastal protection. The go-tos for that are mangroves, coral reefs. Could also talk about seagrass meadows. For coastal protection. From flooding or erosion. So like mangroves and corals, they will absorb the wave energy so that it's kind of like taking the first punch from the waves before it hits the shoreline, thus decreasing erosion. And seagrass meadows, they're healthy. They will be able to anchor in the substrate and hold down the soft substrate from eroding. Within that, these are also, they are nurseries, like the 3 that I just mentioned, for marine species. And let's see, nurseries for marine species. So essentially they are like a nursery ground for like our food sources. Genetic diversity, stable ecosystem, future food supplies. All right. These places are homes to keystone species. And again, these areas are homes to keystone species. Keystone species extinction disrupts food webs or stability. This would be due to a lack of predator-prey balance. And it's not in the mark scheme, but I would probably give an example. So I would say, example, kelp, urchins, and then otters, with otters being your keystone species. Some keystone species could be those that organisms depend on for transportation. Some organisms depend on others for transportation, so it moves their own species around. An example of this would be like barnacles on whales, or the shells of turtles. But whales are much more migratory and transient than turtles are. Some species are sources of medicine for us. Stable biodiversity ensures a future food supply. Stable biodiversity provides for genetic diversity, or more genes or alleles available within that species, which is good because then if there is like an environmental disturbance, they're going to have more than likely more genes that will allow them to survive that disturbance. Stable biodiversity, I think, is important for tourism and the fishing industry. To generate money or income, because that is, first of all, a terrible M, but that's like an American dollar sign, this. So, I mean, saying income is good, and employment. You're almost done. Producers provide climate control. By absorbing, you could call them like a carbon sink. I'm getting sloppy, but my hand is tired. CO2 and releasing oxygen in photosynthesis. Along these lines, this would be the same time you'd want to talk about decreasing ocean acidification, or you can make it your own mark. Then if you have any other very specific one, you could say, like maybe you wanted to give an example of medicine, you may get another mark for that. So I know like the keyhole limpet, hemocyanin is used for, I think it was for Alzheimer's. All right, and so that is the full review of paper 3-2 from May, June 2022. The only thing they don't have in here is like ramp ventilation, pumped ventilation, and regulating osmotic concentration. So osmoregulation. And yeah, that's the only thing else I don't see in here. it's possible it's on the October November paper as well. Good luck tomorrow.